Okay, so hey everyone, my name is John and this is Uma, and we're both currently summer residents at 0xPARC, working on various things in ZK. For the past few weeks, we've been thinking a lot about building ETH2 Light Clients on the EVM. And specifically, we've been thinking about how to use ZK to significantly reduce the costs of running a light client on chain. Furthermore, while Uma and I are the ones presenting, this is joint work with Yi-sun, Jonathan Wang, and Brian. So shout out to them as well. So to give a brief outline of what we're going to talk today, we're going to first start off by talking about how to build this light client from a technical perspective. And then we're going to talk about how this light client can enable new interesting applications, such as building a secure bridge between Gnosis chain and Ethereum. And we think that this bridge can be much more secure when compared to multi-sig bridges, which are used today. So first of all, for people who don't know, what exactly is a light client? Well, a light client is essentially solving the problem that when you want to query information about Ethereum, there are a lot of strong trust assumptions in play. So let's say that you're on a low computation device, such as an iPhone, and you want to know how much ETH you have in your wallet. Well, the naive way to figure this out is that you ask this question to a full node and it returns an answer. However, the problem is that you're completely trusting this full node to return an honest answer. And if the full node is an adversary, he can return an incorrect answer, and you'll basically have no idea that this answer was incorrect. Thus, many early blockchains introduced the idea of a light client, which allows you to query Ethereum state with some sort of validity proof that the answer you're getting back is correct. So in the case of Ethereum, these light clients often store these things known as block headers. And inside these block headers, there's this thing known as a state root, which is essentially a commitment over the entire state of the Ethereum blockchain at some block. After we have this state root, we can actually query the full node with the exact same question. And when returning an answer, it can return a Merkle proof proving that this answer is correct. And the nice thing about these Merkle proofs are that they can be efficiently computed even on low computation devices such as iPhones. So concretely, what a light client has to do is it has to keep track and verify these block headers. So as the Ethereum network is producing blocks, these block headers will be broadcasted to the light clients, and these light clients will have to verify the consensus mechanism of the blockchain. In the case of Ethereum, it's just a proof of work equation, which can be also easily verified. Now, I want to note that Ethereum full nodes have to store the entire Ethereum state, which is in the order of hundreds of gigabytes to terabytes, while these light clients only have to store the block headers, which is significantly less information. Thus, to recap, light clients essentially enable for one to securely query Ethereum state while requiring significantly less compute resources than running a full node. So why would you even want to build a light client as a smart contract? Well, this is because having a light client implemented as a smart contract essentially allows you to implement cross-chain communication. So if we have a Gnosis chain light client contract implemented on Ethereum, this allows you to ask questions on chain, such as, did I deposit 5 ETH on Gnosis? And if you provide a valid Merkle proof, the light client contract can actually answer this question confidently. Now, zooming out a bit, what this smart contract essentially has to do is has to verify the consensus mechanism of one chain on the execution layer of another. So in the case of Gnosis chain, which is using ETH2 proof of stake, we have to validate the proof of stake mechanism in the execution layer of Ethereum. So specifically in ETH2, they have a consensus mechanism specifically for light clients, known as the sync committee, which essentially signs block headers for light clients. And how this specifically works is that there are 512 validators chosen every 27 hours randomly by something known as the beacon chain. And these validators will, for every block, produce an aggregated BLS signature over this block header that eventually gets broadcasted to the light client. And this aggregated BLS signature will only be verified if enough of the validators vote on it. So if we want to implement a light client on chain, a core primitive that we need to do, a core primitive operation that we need to do is actually verify this BLS signature inside a smart contract. However, the problem is that there's very poor support for the elliptic curve operations needed to verify this BLS signature, which makes verifying the signature very expensive from a gas perspective. Thus, our key insight is to move the verification of this BLS signature off chain with the ZK stone.
Yeah, so as John mentioned, we're basically trying to make an ETH2 consensus light client on the EVM, and we're going to make it more gas efficient by verifying the BLS signature with the ZK snark. So basically what's happening is before, remember, we had like the red section that was verifying the BLS signature, which is expensive. Now we're just going to verify a ZK snark proof that will verify the signature for us. So the snark is generated off chain, and then on chain, we're just doing the verification. And verification of a proof on chain is pretty cheap. It's like 200K gas. So what actually goes into the snark? So the first input is just the public keys of the sync committee. So remember, John mentioned that you have the sync committee that rotates every 27 hours that has these like public keys, and those are the ones signing like the block header. And then ETH2 consensus uses a serialization format called SSZ. So another input is the serialization of the block header, which is the message the sync committee is signing in aggregate. And then the last input is the actual signature of the sync committee. And then in the snark, we're just verifying the BLS signature. So we're verifying this like aggregate signature of all these pub keys with the signature and the message like checks out. And then we just output whether or not it's valid. And then on chain, we just verify this proof. And so this is just because of the succinctness properties of the snark, even though this is expensive in the snark, the on-chain verification is really cheap. And so we can actually do other things because inside the snark, because verifying a snark is the exact same gas cost in spite of how much computation can go in the snark. So there's other stuff in the Light client that is really expensive right here. So there's other stuff we have to do, like verify the inclusion of the sync committee in the current block header to update the new sync committee. And that can be expensive. So we can also wrap those computations, for example, here, like verifying the existence of the next sync committee that's attested to in the current block header, and also put that in the snark. And so to put that in the snark, we have to implement this like serialization SSZ inside CircOm, which is like what we're using to make our snark. And we have to have our circuit include that as well. And so to keep the Light client updated, you need an operator node that will basically periodically ping the Light client smart contract with the block headers and the signature and the public keys. And also the operator node will be in charge of generating the ZK proof and sending it along with the rest of the information. And we estimated that the gas cost of this would be like 0.08 ETH per ping. So you don't need to ping the Light client contract every single block that you want, right? So you just ping it on whatever block headers that you want to live on chain. And so because anyone can theoretically submit a new block header, because if you're running a node, you can get the requisite information and generate the proof. This Light client is censorship resistant, and also it has higher safety. So one thing to note here that's pretty important is that the safety of the Light client is only equivalent to the source chain's consensus. So if I'm running a Gnosis Light client on the EVM, Gnosis chain could be very insecure and have a bunch of reorgs. And so maybe I could be correctly updating the block headers, but if there's a reorg on the source chain that you're updating, then the block headers on the Light client are invalid. So that's like one thing to note, is that you're only going to have the security of the weakest link if you're bridging across two different chains. So it's not like, oh, because we have a Gnosis Light client running on ETH, like suddenly, oh, Gnosis Chain's Light client is as secure as Ethereum or something like that. Okay, so we kind of talked about the Light client, and so now we're going to talk about how you actually use this Light client to create a bridge between Gnosis Chain and Ethereum, or for that matter, any chain that uses ETH2 consensus and Ethereum. Okay, so to build a bridge, on the Gnosis side, you have a deposit contract. And then on the Ethereum side, you have a withdrawal contract that will call the Light client contract. So if I'm trying to bridge from Gnosis to Ethereum, I would call the deposit contract and I would put in a deposit. And then in the deposit contract, in its state, we would just keep track of a list of who's deposited, the addresses, the amounts, and a nullifier. So that just lives in the state of the Gnosis Chain deposit contract. And then when you go to withdraw, you basically submit a transaction to the withdraw contract on Ethereum, and you put in the information of your deposit state, and you put in a Merkle proof that that deposit state exists in a certain block header. And so then the withdraw smart contract will call the Light client smart contract and get a header. then it'll check that your deposit proof is valid. So with the Merkle proof you're submitting, and then it's going to check that the nullifier is not in like the series of nullifiers to make sure that each deposit only gets withdrawn once, and then it'll send you the Ethereum. So it's a pretty elegant, lightweight design to actually withdraw. And one interesting thing here is that you can also include this withdrawal function in ZK. So instead of verifying the Merkle proof and the deposit on chain, you could also put this in a snark and verify and only verify the validity of the snark. And then one interesting thing is you can make your withdrawals anonymous. So you could have basically like a tornado bridge where every withdrawal is anonymous to like a fresh wallet. And so just to cover the trade-offs between this light client bridge and the multi-sig bridge, most bridges these days are multi-sig. So just to go over multi-sig bridge, you just have a multi-sig bridge that's centralized, and it, examines the state of both the chains and then releases funds on one chain if it sees like a corresponding transaction exists in another chain. So the pros are it's really fast, it's like super centralized, right? And it's very low gas cost because all the verification of the states of both chains occurs off chain. The cons are there's numerous hacks like Axie Ronin bridge, Harmony, Wormhole have all had many hundreds of millions of dollars stolen from the bridge when the multi-sig gets compromised, and has very low security guarantees because it's like centralized entity and it's censorable. Like the multi-sig at any time can just decide to not release your funds. With the light client bridge, you have much higher security guarantees and it's censorship resistant, as we covered. Some of the cons are that it has higher gas costs because you have to have this operator node paying the light client contract and keep the light client block headers up to date. It's also higher latency because you probably don't want to ping the light client contract every single block because that's extremely expensive. You probably only want to do it periodically. And then another thing is it's less generalizable because you basically have to implement a new smart contract light client for every single different consensus algorithm you'd want to bridge, which can be annoying. And yeah, so John, me, Yi, Jonathan, and Brian are all working on this. And it's the reason we kept on mentioning Gnosis is we got a grant from Gnosis to design a prototype of this like ZK-enabled light client and a ZK-enabled bridge for them. And so this is funded by Gnosis and 0xPARC. And then Brian is also going to talk about this new funding model known as 50/50.